technology organizations are moving away from traditional waterfall development workflows and towards Agile DevOps software development practices. Originally introduced in enterprise, IT, and data center contexts, these methodologies have made their way into embedded engineering organizations, but at the potential cost of software quality. Can embedded tech companies, especially safety and security critical ones, afford to sacrifice quality for speed? Brandon and Rich debate. Later, the insiders are joined by Yannick Moy of AdaCore to discuss how the MISRA C coding standard, which was originally developed in 1998, is holding up given the complete overhaul of automotive and other technology stacks since the standard's inception. Is C, a notoriously compliance-challenged language, still the best bet for safety-critical systems that are now operating alongside a host of other connected applications? Finally, Perry Cohen looks into the true cost of bad software in this week's Tech Market Madness. After reviewing Herb Krasner's The Cost of Poor Software Quality in the U.S., a 2020 report, he finds out just how much defunct software projects, bad legacy code, and operational software failures set back the industry, and considers how DevQual Ops could help recoup some of those losses while maintaining time to market.
Welcome to another edition of the Embedded Insiders. I'm Brandon Lewis, Editor-in-Chief of Embedded Computing Design, and I'm here with Rich Nass, who is a dumb house owner. What's a dumb house? What's a dumb house?
Oh, you're just piling on me today, aren't you?
It finally happened.
It finally happened. I have quite a smart house 99.9% of the time, but it becomes a very dumb house when the internet goes down, and that is the case right now. My whole neighborhood is down. If it was me, I could probably figure it out, but my whole neighborhood is down, so pretty soon it's going to get dark, and I'm going to be sitting here in the dark because I don't know how to turn my lights on. I have to run out and open my garage door because I'm not sure how to do that either. Hopefully it'll come back on.
99.9% of the time. That's only 3 nines reliability. You need like 8 nines reliability if you're going to have a smart house. Well, moving right along. One of the things that we've run into a lot over the past couple of years is the desire to use Agile and DevOps in the embedded space. Obviously, Agile and DevOps and this whole shift left development philosophy is something that was born out of enterprise IT. And it really means, let's just code. Let's just code and worry about everything later. Let's worry about QA later. We'll just code, release, address bugs, as they come in after the release, and then, rinse and repeat. And that's okay in certain industries, or is it? What are your thoughts on that whole movement, Rich?
Okay, well, when you talk about Agile development, there is no better argument that I could make for Agile development than it was backed by Jack Gansel, who knows more about embedded developing than anybody I have ever met in my life. He used to teach courses on this at the Embedded Systems Conference years ago, and he was a huge backer of it. So if it's good enough for him, it's good enough for me.
Okay. Well, I mean, when you think about, an iPhone, that's great. What are the possible repercussions? We're more worried in the consumer realm about getting things to market quickly and features out there in the hands of users than necessarily the bugs that might happen, because there's not much at stake, right? But when you
be careful with that one. I don't think I agree with that. I don't think that people are rushing to market with an iPhone, for example, and saying we'll fix it later. There are definitely examples of that, but a smartphone is not one of them. An automobile is not one of them. Anything medical device is not one of them. I think the field of that is much smaller than you're making it sound.
I totally disagree. Go look at your last update on your iPhone or your Android. What does it say? Version 12.1.2. What are some of the things included?
Yeah, but that's not because it was rushed to market. That's because things have changed over time.
that's not always the case. I mean, there are a lot of bugs that are identified and addressed in the next version.
Okay. All right, I was trying to think of the joke about bugs and I couldn't think of
it. So, all right, jokes aside. So you're doing development in this fashion. You know what? Like, obviously, if your goal is to get new features out to market more quickly, Agile development makes total sense. You're doing Agile, you're doing DevOps, you work in sprints, and the philosophy is, you know what? We'll fix it later. You know, a lot of these things aren't even going to be found anyway until they're out in the wild operating. But when you're dealing with an embedded system, like your point earlier about a car or a medical device, you can't do that. Nevertheless, there is the desire to want to speed up these embedded development workflows, move off of your traditional waterfall model into Agile development. Is that a good thing or a bad thing?
And let the world be your beta tester.
Correct. Is that a good thing or a bad thing?
Yeah. It depends on the application for sure, but there are many instances that you just can't replicate in a lab, and you really have no choice than to just let it go. And when it happens out in the real world, then you figure it out. Unless it's life-threatening, mission critical, I don't have a problem with it. Updates happen, you know, when you plug your smartphone in overnight. These things are happening like all the time, and they're happening to cars. I don't have an issue with that. I'm good with that. If it gets it out the door much quicker and with more streamlined code, I'm fine with it.
Okay.
Because it does usually lead to that. It does eliminate, not eliminate, but narrow down code bloat.
So you're fine with it. Are the companies who are actually putting their neck out there fine with it? Because, you know, the alternative is you become SolarWinds. You become, you know, pick your IP camera vendor. You know, you become the GOAT. You become the butt of the joke who it's, oh man, you know, those guys don't take their coding seriously or their security seriously because they got hacked because they were pushing stuff out so quickly they weren't even checking their work, right?
Well, but you have to separate features from security. But I mean, you're talking about if your camera doesn't pan correctly versus being hacked. Those are two very different things. And we're at the stage now where security is not that hard. You just have to want to do it. And I think you need to separate that from the rest of the discussion.
Well, are they? But I don't know that they are two different things necessarily, because we added a feature that allowed your camera to pan more smoothly. And in the process of doing that, because we had to get this out to market before competitor B, we cut some corners and we put some buggy code into the system and we left a back door open.
Is this where we agree to disagree? Because I don't think that's happening. I don't think it's that easy to leave your back door open like that if you're working securely.
Oh, I mean, I don't think people are trying to do that. But, you know, here's my good old friend, the internet, always there to save the day and believe everything you read on the internet. So I just did a Google search.
That Abe Lincoln.
Right. I just did a Google search while we were talking, and in the last day, I found 6 or 7, still going, 6 or 7 articles here about software vulnerabilities that could affect an embedded system. One here is talking about SolarWinds. Another one's talking about something in remote code vulnerability in the Python language. Another about all these 223 vulnerabilities that were used in ransomware attacks. Another one in the Java runtime. Another one in Node.js. So, I mean, everybody's using this stuff.
Yeah, but I think I'm going to go back to how you started this discussion. And Agile development doesn't mean get it out the door really quickly with bugs.
Right. It doesn't. But what I'm saying is that I think that there's a higher propensity for that to happen. And so how do you make sure that you're putting in quality checks like you would for an embedded system, or not just an embedded system, let's say a safety critical embedded system into your Agile development workflows, or can the two just not coexist at all?
They can definitely coexist at all. Yes, they can coexist.
They can coexist. How would you do that? Do you need to put your static analysis checks in after every I don't know, portion of your sprint? I guess maybe that's what it is.
Yeah, I would think it would be done by different teams, and each team has the responsibility of their subsection of code.
So then you're waiting on the QA guys, right?
Well, you have to self QA.
And then here we are back at the beginning, right? Because all of these things to make sure that your software quality is high enough necessarily add time, which seems like the antithesis of what you're trying to accomplish with Agile.
Yeah. Yes and no.
You could introduce code that is not safe, but you could also introduce code that is vulnerable, right? I mean, and that's obviously the top of mind for a lot of organizations right now.
Well, you're actually bringing up a whole nother subject, and this is a subject that I think we're going to get into next week on the next edition of Embedded Insiders, where we talk about you are going to get hacked. I think the world has come to that realization. So now I need to make sure that when that does happen, I'm ready for it. So tune in next week, same bat time, same bat channel to hear how that works.
The Insiders are joined by Yannick Moy of AdaCore.
So Yannick, when was the last time that MISRA C, the coding standard, was updated, and what's the purpose of it? Actually, maybe I should turn that around. Can you remind the audience what MISRA C is used for, that set of coding standards, and then when was the last time it was updated?
So MISRA C comes originally from the automotive industry in the UK, but it has been adopted since then in a variety of industries and is still quite strong in the automotive industry. And the first version was in '98, so quite some time ago. The second version was in 04, so 2004, and I started to get interested in that at the time because I was already doing static analyzers for C, C++. And I got more involved in the latest version from 2012, where I was part of the official review efforts. And this last version is really quite interesting. So it doubled the size of the documents, in particular because it came with a lot of rationale and examples to explain why these rules make sense to make the code safer, more secure. So it's a coding standard really focused on producing more secure, safer software. It's only a 10% increase in rules from the second to the third version. But really what came in this third version is a lot more explanations so that people can judge for themselves if the rule makes sense in their context. And more division, more explanation of what goes in each rule and when or when not to apply them.
So one of the things that's really interesting to me, at least, is that now we're using MISRA C 2012, but it's 2021, and since 2012 there have been a ton of updates in the automotive sector in particular, and I know MISRA C is also used outside the automotive sector to some extent, but just within the automotive space, connected cars, that's now a given. Putting in these really big sort of almost data center class electronic control units to execute workloads like artificial intelligence, machine learning, a lot of really cool in-vehicle infotainment stuff. So now you've got these heterogeneous systems. You've also got a lot of new types of software that are in the car that may not be written in C, may have been written in higher level languages. So with this 2012 rendition of MISRA C, and now all of this new technology coming into the car, don't you think it's time for an update? Don't you think that we need something a little bit new? Maybe just from the point of integrating C with some other type of object-oriented language or something?
Well, there's a lot of existing practices and workflows. So here you also look at the code that is generated. So a lot of code is generated in C. And that's probably why MISRA C still makes sense from this point of view, because what the MISRA C committee said is that what they couldn't put in the C standard, which, as you all know, doesn't evolve anymore, or very, very slowly evolves, they put in the MISRA C standard. So MISRA C can be seen as an extension of the C standard for high critical software. And in that sense, as C doesn't evolve anymore, or very slowly, MISRA C doesn't need to evolve that much. it just gives a bound on what you can achieve with C, because as the foundation language, C is still quite weak in what it provides. And the MISRA C standards acknowledges that. So if you look at it, it says things like ISO C may be considered to exhibit poor type safety. And on top of that, it provides a bit more. So it explains why it has all these vulnerabilities or fallibilities. And it comes with a different type system. So it comes with what they call an essential type system, for example. And they try to forbid some dangerous uses of the C language. But that still doesn't go as far as stronger, safer languages. So for the future, you can perfectly consider that C may not be such a suitable language for hand coding stuff, but it will still be around for generated code. And in that respect, also MISRA C is still quite valuable.
Yeah, so I mean, I think, let me sort of restate what I was saying before. Yes, C as a language isn't progressing that quickly, if at all anymore. It's sort of a slow burn at this point. But that doesn't change the fact that the context within which C is being used, in this case, in the automotive application, in those industries, everything is changing. So obviously, one of the reasons that C was so successful and has been over the course of computing is that it's flexible and you can use it in a lot of different contexts in a lot of different ways. But necessarily, because the applications are shifting and you've got a new set of technologies that are coming into the vehicle, doesn't that change some of the rules around which, I mean, you use C in a safe way, we understand that, but you're talking about now trying to use it in a safe and secure way with the addition of these other elements. Does that change anything?
The other thing I'll throw into what Brendan just said is that the hackers that are out there today, they may even not have existed in 2012, and it wasn't nearly as much of a game, and I'll use the air quotes around game, but it's like a sport to be able to hack into these vehicles now, and that was not around 8 years ago.
But the vulnerabilities were already around in 2004 or 2012 and even before. So the C language is well known for its vulnerabilities, and the MISRA C standard goes in great length at describing what should be avoided. At the same time, it also falls short of providing the same safety as type-safe languages, for example, or memory-safe languages. Mm-hmm. And so here, it's well identified what needs to be done. And so if you cannot move to another language, a safer language, MISRA C provides you some boundary, and it still has some rules like the famous 1.3 rule that says you shouldn't have any undefined behavior. And having undefined behavior is the plague of C programs. It's very, very difficult to avoid undefined behavior, and essentially, if you have some of it, like accessing out of an array or doing an overflow on assigned integers, then you know that with some compilers, with some optimization, you might have some problems in your generated code. And well, we see that's the most you can have.
So even despite the fact that MISRA C does provide some level of at least recommendation, you did mention that there are a lot of vulnerabilities. In some of these memory-bound applications, C can be vulnerable still. What is the path forward then if you're trying to develop let's stay in the context of vehicles again, if you're trying to develop a modern vehicle, you still have to use C because you have however many millions of lines of code of C already written. What do? What's your path forward to make sure that these advanced vehicles are still meeting the safety requirements that you need?
So I believe that vehicle manufacturers already have solutions in terms of architecture of the system to make sure that vulnerabilities don't have the same impacts wherever they are in the code. So you can isolate pieces that must be safe and secure from pieces of code that don't have to apply, for which you don't have to apply the same requirements. But for anything new, I would say moving to a safer language is still very valuable. And MISRA C also helps you figure out why you would still go with C and what is the cost of that for the highly secure software that you need to that needs to behave correctly. And I've heard in your podcast, so some mention recently of other languages in embedded software development, and that's true for automotive too. So moving to Rust, to Python, to Ada, Spark has some value because it avoids all these vulnerabilities from the start, or provides the tools to avoid them. And so C might still be a reality in some contexts, but not necessarily for the 10 years to come.
So if you were to move from C to one of these other languages, I mean, what does that look like? Aren't you, I mean, are you essentially starting from scratch, like starting a new fresh code base and eventually just chipping away at that big mountain of C code that's already exists?
So I believe all of them provide some low-level interfacing with C. At least so in our case, we're developing tools for Ada and Spark, subset of Ada. It interfaces natively with C, and our customers in the automotive market who adopt our solutions, they just replace parts of their code with Ada or Spark as time goes by, and replace code essentially.
Mm-hmm. And so what right now are you seeing as the key subsystems where Ada and Spark are being used as a C replacement in automotive? Is that, like, I don't know, brakes or steering or, anything in particular?
Yeah, these kind of things. Yeah. So two customers that I can talk about because there were press releases, they are official about that, is NVIDIA. So NVIDIA in their platforms for the embedded and autonomous driving, they're using Spark, and they're using Spark for their most secure software, most secure firmware. And one of the guys was the security reviews at NVIDIA, Dawal Kumar, say that for some of these codes, they had to go through multiple security reviews to make sure there's no vulnerability left. And the use of Spark allows them to check this box saying, okay, this kind of vulnerability like buffer overflow, it's gone from this code, and we can focus on something else like higher level security review. Another one is Jetex, Japanese manufacturer, and they are one of the leaders in steering wheel systems. And they use Spark in the safety context. So contrary to NVIDIA, which has also a big focus on security. And in this safety context, they want to make sure that whatever requirements are implemented in the software for the steering wheel control is correctly implemented. And so they can check that all these requirements indeed are enforced by the code using the capabilities in Spark.
Yeah, so I was just going to ask, what are those capabilities in Spark? What sets Spark aside from C in the context of these applications to make it more safe and secure?
Yeah, so at the level of MISRA C, they provide guarantees that something like MISRA C and the tools that check MISRA C cannot provide. So for the rule that I mentioned before, no indefinite behavior, this is something you can enforce in Spark because the language allows that. The language is based on Ada, so with a strong typing from the start. And the tools make sure that there are no buffer overflow, no overflow of signed integers. So you can get a strong guarantee here that there are no vulnerabilities that attackers could exploit. And at the next level, if you want to do something like what Jetex is doing for the steering wheel, you can specify properties on the code. So you can specify contracts on the code. You can specify invariants, things that the data must always obey, and the tools will make sure this is okay or let you know about it.
But oh God, Yannick, now I've got to go learn another language, right?
Well, Brandon's still young enough to learn a new language. I'm still working in assembly code.
Oh, Rich keeps telling me I got to do things in ladder logic.
Finally, Perry Cohen looks into the true cost of bad software in this week's Tech Market Madness.
We all know that flawed software can be expensive, but just how expensive? According to the Cost of Poor Software Quality in the US, a 2020 report, that cost was more than $2 trillion, and that was just in the US alone. The report, produced by the Consortium for Information and Software Quality, or CISC, is broken into three categories. Unsuccessful software projects, which accounted for $260 billion, poor software quality in legacy systems, another $520 billion, and operational software failures, $1.56 trillion, up from $1.275 trillion in 2018. Okay, we may be able to deal with the $260 billion in unsuccessful software projects. That's just a general risk. But poor software quality in legacy systems and operational software failures, these are serious issues, even when they don't affect embedded systems that could potentially cause damage, injury, or even death. How is it possible that software quality is falling so short across so many different dimensions?
Here is a big problem. We think it's about this big. It's mostly unseen and unquantified and perhaps uneven undiscovered in most organizations. And you all really should start paying attention to this area. That's kind of what's behind, why we did the report and why we bothered to try and estimate the cost, because people pay attention to dollars, quite frankly.
Herb Krasner, the author of the report and CISC advisory board member, compiled data from 88 different sources as background for the report. He says that software is growing at a rate of approximately 111 billion lines of code each year, and that even the best software engineers commit at an average of 25 bugs per 1,000 lines of code. So, more software, more flaws. Got it. Well, it's that and cost and speed to market, as Krasner explained.
What they've been pushing, is a continuous cycle of getting releases out the door without necessarily paying good attention to quality. So perhaps there's more suspicious software being developed and produced even today than there was in the past. Most of the Agile development teams, they focus on features. Okay, here's the list of features that we want to implement for this sprint, let's say. Okay, and they don't necessarily leave the appropriate amount of time for fixing the bugs that pop up during that sprint. In fact, they often defer those to a later sprint. And then they may or may not get around to it.
So, what can be done to reverse the course of costly, faulty software? Obviously, developers can start by catching defects earlier in the development stage, but we've all heard that before. And slowing down development to catch bugs works at cross purposes with the whole Agile DevOps practice, doesn't it?
What I'm advocating is, to that model, we add specific quality requirements or quality objectives. We measure and track to those. We consider those as well as the user stories we're trying to develop features for. We leave time in each sprint for fixing bugs.
This is where DevQualOps comes in. It's similar to DevOps, a continuous loop of Agile development coupled with the idea of continuous delivery and continuous or frequent releases. Only DevQualOps addresses the quality of the engineering activity. In the DevQualOps model, there are specific quality gates at the end of each of the phases of design, development, and testing. So there's an explicit quality check that must go in along with these ideas of explicit quality engineering. Products don't need to be rushed. They need to come in waves, Krasner added. Developers need the time to implement quality control practices, identify bugs, and fix bugs. And organizations need to balance their time to market goals with the simple fact that software remediation becomes more and more costly the further you get into the development and product lifecycle.
It actually costs less to develop good quality software than it does to develop poor quality software and get it out the door quick. And one of the reasons behind that, and one of the reasons it's been problematic, is because it's been difficult to measure software quality.
Thanks for listening to this edition of Embedded Insiders. For daily industry news, videos, and podcasts, visit our website, embeddedcomputing.com.